Hello, everyone. Welcome. My name is Dee. I'm from Tetrate. I'm one of the Envoy maintainer. Today, I'll talk about the extending Envoy with WebAssembly with John from Google. So I'll do the introduction on how we extend Envoy in the current state, and then we will try to introduce new plugin system. I can say that a new way to extend Envoy using WebAssembly. So this is today's agenda. It's about Envoy. I mean, it's like a quick recap on Envoy. I mean, it will. So please bear with me. It's an invitation for all of you to basically try to contribute to Envoy. And then after that, we will go down to talk about a little bit about Envoy architecture itself and how it can be extended. And of course, we will go to the core. It's extending Envoy with assembly. John will do that for us. And there will be a demo. It's hopefully a good demo. It's a live demo. So, and then we will do a Q&A. So the promise of Envoy is network should be transparent to application. So we believe that developers should focus on the business logic. I mean, developers should only deal with the application logic, not thinking about the network itself. So, but when some problem occurs, it needs to be very, very apparent where is the problem. I mean, like if the problem is in the application logic itself or in the network layer. So Envoy itself is a very high quality code base and the speed. If you see the speed of the project on GitHub, it's very, very fast. And then it's designed to be extensible at its core. It has eventual consistent configuration API. If we have this XDS API, we call it. It's LDS, CDS, and stuff like that. And no open core paid premium version is all there, everything. So in Envoy, we believe that, again, this is an invitation. So we believe in community. So people can come up with ideas, put some proposal in our project, and we will make it happen. So who is Envoy? So basically, this is the talk from Harvey, the last EnvoyCon. So as you can see, that Envoy consists of many contributors from many organizations. But as you can see here, you can see Turbine Labs. Turbine Labs has this contribution on thrift filters. So it's an extension of Envoy. So as you can see, if you do extension, basically you will be on top of the contributors. So to know Envoy better, on Tuesday, you can go to the Meet maintainer. Lizan will be there. And then the next day and Thursday as well, there will be intro to Envoy and deep dive. So again, so this is the Envoy architecture. Envoy is structured like this. So basically, there are some workers running to accept the connections, and then after that, there we go to the listeners. So here, in the listeners, here is the first extension point that you can do. So if you go to the Envoy source code tree, there will be an example of listener extension is TLS inspector, for example. So basically, you can dealing with the read and pick the before you accept the connection. And then after that, you go down to the L4, the TCP stack of Envoy. Currently, Envoy only work on TCP, but the UDP part is in progress right now. So after that, we have these L4 read filters, and to read the bytes in and bytes out. And then we do have these L4 write filters where you can actually like mutate the traffic. And And here, so basically the L7 itself is built as a network filters and L4 filters. So you can have like L7 filters like HTTP or TRIF or probably MySQL. Right now we have MySQL, but not necessarily, it's only like read filters. But of course you can do like write filter for any protocol you want. And then inside that L7 layer, you can have another stack of filters. So that's another extension point. So you can write your own L4 filters, and you can also write your own L7 filters. Envoy itself has many other components, like auxiliary components, like stats. So you basically can have stat syncs. I mean, in Envoy, we have many options of how you send stats out, like statsd or Prometheus endpoints or many other things. We have also like the XDS API, as I told you before. So to emphasize this, that Envoy is designed to be extensible with multiple extension points. As you can see, the very obvious thing is you can put your extension on L4 and L7 as L4 and L7 filters. You can basically pick your traffic, or you can also mutate your traffic. Envoy also allows you to have your own access logger. So we have like defined interfaces for you to build your own access loggers. We also allows you to bring your own tracers. We have Zipkin, we have open tracing, we have a couple of things here. Even we do allows people to extend health checkers. The current example right now in Envoy 3 is on like Redis health checker, but basically you can build other things. And another interesting thing is probably like retry policy. Probably in different organization you need a different way of retrying requests. So if you go to Envoy source code GitHub repository, you can see that you can go to Envoy source and extensions. You can see it's growing and growing. You can actually like introduce your own if you want. So basically, the structure of an extension is consists of business logics, how you read the data, the bytes, or in a higher level like L7 HTTP, the how you actually read the headers, the body or the trailers, and how you actually manipulate those data. But another thing important is the configuration on how that filter to behave just like what you want. The problem with this is you need to introduce this. I mean, the code, the business logic, it should be inside the Envoy. Currently, it only can be introduced inside the Envoy code structure. It should be statically linked. But later we will introduce the WebAssembly where you can actually dynamically load some logic, put inside the Envoy, and then run it to manipulate your data. So yeah. The configuration in Envoy is represented as a proto tree. Protobuf tree is very interesting technology. So basically you can, for example, like in your organization, you need this out service filter. Probably you don't want it to be upstream because it is very specific to your organization. So you can have your private extension to be configured like this. So yeah, as I said that to write your own extension, currently we can do it using C++ or Lua, but Lua has some limitation. Currently it is only for HTTP traffic. Of course, it can be extended to L4, but Lua is, if you deal with some kind of, you embed another runtime inside another process, you will have another problem. So this is an example of gzip filter in C++. I just want to very quickly to go on what we need to have your own filter inside Envoy. So in gzip filter, basically we have this. This is how you plug in the configuration. As you can see here in the gzip filter config, you get the Envoy, the gzip specific configuration. It's defined as a protobuf message. And then you can load the configuration that is needed by the gzip to behave. So in the HTTP stream filter, basically, we have several things to be overridden. The first one is a decode headers. That is the decode thing is when the data comes inside Envoy. So basically, when you have this HTTP request coming inside Envoy, and then you do this decode headers, you basically see what is inside the headers, and then you can do the decision on what to do when you see a certain headers. And then decode data is doing with the data, and the trail is also the trails. So in the case of gzip, basically, if decode headers, probably like you see that, the request wants you to respond with compressed data. So you can see it from the decode headers. By having that information, you can send it back through encode data to the caller as a compressed bytes. So this is what I said before, that the decode headers in gzip filters is basically the first one, very simple. If it is enabled, or it is if you configure it to compress its response, or it has the except encoding headers, something like that. So you can basically sending back the compressed response. This is the encode data that basically send you back the compressed information. So basically, currently, seems like we can do better than this, right? So probably we can introduce some plugin mechanism that is dynamic enough and easy enough for us to integrate it into our workflow in the organization. So now I'll invite John to talk more about extending Envoy with WebAssembly.
Hi, I'm John Plevyak from Google, and I'm going to tell you a little bit about a project I've been working on, which is to add WebAssembly VMs into Envoy and stitch it in through all the different extension points. Currently, we have several extension points done, and I'll tell you about those and some of our future plans as well. So I'm going to start by talking about the overall architecture, how the VMs are placed within the Envoy process. I'm going to talk about the different extension APIs that we're supporting and how the VM API works and the way that anybody else could add a new VM support. Currently support WAVM and V8 and what we call the null sandbox, which is a way to link in your extensions directly, but using the same APIs that you would use if you're going to do it in WebAssembly. And that will allow you to put your extension under a standard debugger and not have to deal with the sandbox during your debugging phase. So the first question is, well, why WebAssembly in the first place? Well, it has a bunch of advantages. One is it's portable, and in this sense, I don't mean that you can move the code around, but that you could take a WebAssembly module and you could run it inside Envoy, or you could build a similar environment. You could run it inside Node, for example, if you wanted to test it there, or if you wanted to use it in a different environment. It's also sandbox machine code, so it has advantages there in terms of protecting yourself. It's a web standard that's under active development. There's a whole bunch of new extensions coming out with threads, WASI support, which is a generic OS API support. Different tool chains are available. It's got good languages support, TypeScript, C++, Rust, and a variety of other languages in different states. And because it's being actively developed, we expect that, once, for example, the GC support gets standardized, that we'll see, other languages like, Java and Go fully supported. It's also pretty fast. So, we can expect performance of about, 60, 70% of what you'd expect out of native C++ code. And it's relatively safe. So it's sandboxed. You could also add additional levels of sandboxing to it to make it even safer. And finally, one big advantage is that it's portable in the sense that you can move code into a running Envoy process and dynamically link it in. And that's really nice because it allows us to modify our extensions without having to restart Envoy itself. So let's consider what use case you might have for something like this. Let's think about the use case of Istio, the service mesh. So Envoy is used in the data planes to enforce Istio policy. But by having WebAssembly extensions, we can avoid having to modify Envoy itself, which is a real big advantage because you can run on the standard code base. And it also means that you can avoid certain network hops during policy checks. So you can cache a lot of data locally without having to make a gRPC request to, say, Mixer. You can also avoid restarting during dynamic reloads. You get some isolation, which is nice. So if your extension crashes, it won't necessarily take down all of Envoy. And if you've got certain extensions that are pinned to certain flows, then they'll only take down those. And also you can do A/B testing. So I'll go over a little bit of the architecture and the APIs that we have. So there are three types of APIs. There's general APIs, those are the ones exported by Envoy itself, things like logging, stats. There's also extension APIs. Those are like filters, L4 filters, L7 filters, logging filters. And finally, there's the VM API that you'd only use if you're going to add support for another VM system into this project. So you don't have to really understand this whole slide. I'm going to have different slides to break it down. But this is the overall architecture. In the big area in the center here, we've got Envoy. There's a variety of VMs in there and subsystems. And it's talking to the other mesh nodes over here on the left-hand side and the control plane. Now I'll break it down. So this is how we configure VMs in Envoy. So initially, when you start up, you've got your normal Envoy YAML file that describes all your filters. And in there, you're going to have a description that says, hey, I want to have this VM, and I want it to have this VM ID. And that VM ID is going to be used for these set of filters. And you can have any number of those that you want. So you can have a lot of different VMs. And then later on, you can pass in new descriptions, new configurations dynamically using XDS. And those descriptions could include, say, URI and a SHA-256 that says, hey, go out to this code repo, pull down this WASM module. This is the one you want to use. So initially, we'd start out with it on disk, but you could go get it from another source later on. All right. So the first thing to understand about Envoy is it uses silos. Those are single threads that handle a dedicated set of streams. And therefore, the WASM VMs that we have are also going to be single-threaded. So when we describe a VM template in the configuration, that template, if it's used for filters, is not going to be instantiated one VM per silo. That allows us to be single-threaded within the silos and to not have to worry about locks or any other sort of issue. So as you can see, a variety of streams will come in. Some subset of those streams is going to be handled by a silo, and therefore some subset of those streams is going to be handled by a particular WASM VM for any given filter. Now the question is then, how do these things communicate? So we've got all these different sandboxes, but we still want to have, potentially to have collective information. So if you want to have, for example, collective stats or collective policies, if the VMs have to make gRPC calls out or HTTP calls out in order to get specific information about particular paths, when we want to cache that information, we can store it in shared data. that's another one of these general APIs we're providing to the WASM modules that allows us to share data between VMs. And we might also have a situation where we want to consolidate a variety of information, maybe stats or logs, and we want to send these out to some other process. So we're sending them out to Istio or Fluentd or whoever. And so in order to allow this to happen, we can also have services. So services are singletons. So a singleton would be a single VM that runs in the Envoy process that's then used as a consolidator. It can talk to the siloed VMs through shared data or through a message queue. And then it can go take that information, consolidate it, and for instance, send that information out to log syncs, to stat syncs, or any other sort of metrics backend that you might have. Okay, so what kind of general APIs do we support? These are the APIs that are supported by that are in Envoy that represent calls made out of the VM to do some operation that's more general in Envoy. So we have support for timers, metadata of all sorts, of which Envoy has like 7 or 8 different types, HTTP GET, REST calls, gRPC, both Envoy and Google style, logging, stats metrics, shared data, and message queues. And let me give you an example of how these things are wired in. So we want to have multi-language support, and but we also want to have a nice API. And so we've taken the API and we split it into 2 parts. We have a low-level C-style API that's actually supported by Envoy but in the VMs. And it has a format like, I had a pointer. It has a format like up top. So as you can see, things are passed in just as raw primitives. And so if you want to pass any data in or data out, you have to pass it by a pointer and a size pair. And those things are opaque. But for a high-level API, we'd like to have something more powerful, something that we're more used to. And so for each different language, and in this case, particular C++, we're going to provide this set of wrappers. These wrappers are provided just in header files as part of the API. And in this case, you can see that we've taken the low-level API, which allows you to define a metric, which comes back as an opaque integer, and then increment it by by passing back that opaque integer, and turn it into something a lot nicer. So we have a counter that has fully typed tags. We can increment based on providing the information for the tags. We can also resolve that so that it goes back to this integer, which is going to be a lot more efficient, so we don't have to send the string through every time. And then with that resolved one, we can increment it directly. So this gives us an example of how all the APIs work. There's a low-level API that's available to all the languages, and then a high-level API that's specific to each language that follows the idioms of that language. Okay, so what type of extension APIs do we have? Currently, we're supporting HTTP filters, log filters, service singletons. We have definite plans to do TCP filters and log syncs. We'd like to do listeners as well. It just comes down to how much bandwidth we have, who wants what, right? So the API extensions are pretty easy. If you just follow the template of the code, it would be really easy to add another one. So here's an example of what an HTTP filter looks like. Because this is all callback related, there's no threading, so you're not getting a situation like you would in Lua where it looks like you have continuous code. Instead, you just have calls. So there's a context, and that context represents a stream. So that's like one HTTP request, and it has the call out. So like on request headers means the request headers come in, and then you can log. You can make a debugging log call. You can get a header. You can modify that header. And then you can return, your filter status. And as you can see here, this supports actually both an HTTP filter and a logging filter all in one. So, when you're doing your configuration, you configure both of those things. You'd vector them into the same VM, and you'd handle them with the same context. And that gives you the advantage of carrying context through both the HTTP filter and the logging filter, which is a nice plus. Next, we've got the VM APIs. It's really only important for somebody who wants to add a new VM. Currently, we support WAVM, V8, and the null sandbox, which allows you to compile directly into Envoy. And if you want to add a new VM, for instance, you're into Crane Lift and you really want to put that one in, there's only a few things that you need to do. You need to implement a function to register callbacks. These are calls that come out of the VM, all those general APIs I was talking about. You need to add a function to get functions from the VM, so you can get the handlers that the VM has for when a call comes into the VM, like the onlog call. You'd have to have a way for Envoy to get that call from the VM. And then you need the general load, link, and start. And finally, we do everything by copying memory in and out of the VM. That's because that's sort of the lowest level, simplest API. It also means that we can wrap the VM in a process if we want to add additional security. And so you have to add a simple set memory and get memory operations. And once you do that, you could implement a new VM. So what's the status? I think we've gone over this before. A bunch of this stuff is done. We've got several different types of filters, several different types of VMs, several different types of general APIs, metrics and logging, HTTP calls, gRPC calls. And what are we planning to do? Well, we want to do additional extension APIs. We'd like to have additional VMs. There's a bunch of new standards coming out, threads. We'd love to have zero copy memory for those cases that it's appropriate for. And we'd like to have support for dynamic loading and linking. And of course, we'd love to upstream this into the Envoy master branch. It's not there yet. It's something we fully intend to do. So in conclusion, WebAssembly is good for Envoy. It's efficient, relatively safe and secure. It's dynamically upgradable. And we've got an issue to put it in, as well as a repo under Envoy Proxy, but it's not Envoy itself. It's Envoy WASM. It's sort of a sandbox right now. So it's a staging area so that we can get the PRs into upstream. And we'd love to get some contributions. So now I'm going to try to do a live demo. That's always a fun experience. OK. So I think I have a few minutes. OK. So the first thing is the API. So there's a file directory, which is API WASM CPP. So there's additional languages in there like API WASM Rust. And in here you'll see that we've got some .bc files. Those are actually WASM encoded bitcode files for support for protobufs that are pre-built for you. There's also various header files. So proxy WASM extern over there. Those are the external function calls, the general API calls. The impl.h1 is the high-level APIs. And the enums over there are the enumerations that you might see. So let's take a look at, say, the enumeration one. You can see in here that we have the various log levels defined, different header status messages, things like that. I can try. If I do that, all right, I'm going to do the second part of the demo, and then I'll come back and make the font bigger, because otherwise you can't see the log lines. All right, so let me show you how this goes. This is Envoy running, and this is what happens when you run the example. So this is the example that we saw. Well, I'll show you the example in a second after I make the font bigger. But as you can see here, it's actually printing out the log lines for the different callbacks. So on done is when the stream is done. On log is when the logs, when it gets the on log callback, and on delete is when the context is deleted. So we can see that that those logs are coming out. And if you look over here, you can see that we've added a new header called new header. Now let's see what happens when we modify the code. I'm sorry that this is so small. All right, so this, again, is one of those contexts. As you can see, it has like on done, on log, on delete, on request headers, right? So in on request headers, we're going to, well, actually, in on response headers, we're going to modify the response header. And so that's what I printed out before. And as you saw, we added a new header called, it's really hard to see, I'm sorry, called new header. And the value is new header value. And as you can see up top, well, as you saw before when I printed it out, it came back as new header value. And here we're going to just change it. And I'll show you what happens when you have to compile it. So you compile it. It's using the Inscription tool chain. So that's EM++ for the Inscription C++. All the additional parameters are coming out of that make file that I showed you before. Now we've just generated the new code. And if we run it again, and now you can see that we've changed the value now says new header value. So we've compiled new code, we've uploaded it into Envoy, and we've run it, modified it, changed the value. So, and it's, the make file is pretty straightforward. It just refers to the make file in the API directory. In this case, it's the light version. So there's two versions of the protobuf library. One of them compiles down to about 200K. That's the light version. The other one compiles to about 2.5 megabytes. So, if you need that support, and you really want to have it, and you're willing to pay 2.5 megabytes for it, then you can use the full protobuf support. But if you don't need it, the light version is available to you. Yeah, I'll see if I can make these things a little larger. I don't know. Yeah. Well, we could do some questions now while I make it a little larger. If anybody has any. Yeah? Yeah, I think it'll be something somewhere between 50 and 60%. I think that's what V8 and Crane Lift are running at right now.
Is that, so okay, it's part of V8.
Yeah, yeah. So WAVM is different. I would expect that WAVM you can precompile it and it uses LLVM as the back end. I would imagine that with all the flags set, you could probably get it to native if you wanted to go that route.
Yeah. So. Is it working? Just to make sure I understood, right now you have to have the compiled file locally in the file system, or is it part of the configuration? Can it be?
Yeah, it's right now you specify the file name in the configuration, but we're gonna wire it into XDS. So that's like that's definitely happening soon. Somebody's assigned to that, but we just haven't got it.
Okay.
Done yet.
Great. And do you have time estimation for when it's going to be in an official Envoy release?
The code is sitting in the Envoy proxy, namespace. It's in its own repo though because we're talking to everybody over there about upstreaming it, but nobody wants to just take the code, right? I mean, you could take the code, but the community needs to agree that the code is structured correctly and the APIs are the ones they want, right? And once they agree, I'm going to do everything that they want me to do to get that thing upstreamed. So I don't have a timeline. It's really up to the community.
Okay, great. Thanks.
Sure. Yeah?
What's the memory resource usage?
It depends. So, it depends on how much big your code is. Like V8 uses about 2.5 megabytes per VM. So if you have a lot of threads, a lot of silos, then it could add up. Most of that's just because you've got stacks in there. You've got a stack in there, and you've got a heap in there, and you can tune these things down, right? So if memory is really an issue for you, you can and your memory usage. Like these are just the defaults. You can tune it down, or tune it up if that works for you as well. Yeah. Yeah, the only if-def in there is if you want to use the null sandbox, because the null sandbox is actually compiled in. So WASM itself is a 32-bit standard right now, and the null sandbox is compiled into 64-bit Envoy. So there's a difference there. And in addition, in Envoy, we have to be in the Envoy namespaces. So there's like a big block of namespace logic that has to go in around your code. But other than that, there are no changes. So it's actually pretty transparent. Yeah, definitely. I'd love to use that tool chain. I've been playing around with it. As it progresses, I would really like to go that route. Yeah. Anybody else? Oh, yeah. No, it compiles with both GCC and Clang, and it's actually so you can decide to compile in any number of VMs. So you could compile in just V8 or just WAVM, or you can compile them all in. But you can only select one, obviously, that's been compiled in. But that's the only constraint. Yeah. And if you compile in with V8, it takes takes a lot longer to build initially because it has to download and build all of V8, which takes like 10 minutes on a 32-core machine. Yeah, because it's big. But WAVM's a lot smaller. So, but that requires LLVM, which itself is quite large. So, yeah, some trade-offs. Any other questions? Any other questions? Okay. All right. Okay. Well, thank you very much.
Thank you very much.